Hi gals and guys, thanks for checking in again with ViViMaT. Remember when I said that one of the presentations depended on a Nature Communications paper going through? Well, guess who wrote yesterday that it went through? Valentin Salinas, the main author of that paper, whose author list reads a little bit like a who is who of nanotribology. He got his bachelor's in mechanical engineering from the University of Monterrey, Mexico, and is now a PhD student at the Ecole Centrale de Lyon in France. His research is focused on DLC coatings lubricated with liquid additives for automotive applications. So people, consider this dessert.
Coatings is a peer-reviewed journal of coatings and surface engineering published online by MDPI on a monthly basis.
And now, DLC coatings.
Hello everyone, and welcome to my talk here at the ViViMaT Vienna Virtual Materials Tribology Workshop 2021, where today I will be speaking about the interplay of mechanics and chemistry and how they have a crucial role in the tribological behavior and specifically the wear properties of diamond-like carbon coatings interacting with ZDDP-additivated lubricants. This study was made in collaboration with our laboratories in France, where I am currently in my third year of PhD in Lyon, where we conducted experiments, and from our colleagues in the Fraunhofer Institute in Freiburg, Germany, who conducted sophisticated computational simulations. And before I proceed to the rest of my presentation, I would just like to take a moment here to thank Dr. Stefan Eder for his patience and comprehension as I was waiting for acceptance of this paper before we could upload the video. So thank you very much for your patience, and hopefully once the paper is published, we can link it in the description below if somebody is interested in looking at more details to this work. So you are probably familiar with this image where we can see that the total energy that is actually used to move a passenger car is very low compared to the energy that is lost through the different sources in the system. And in this study, we're going to focus on the energy that is lost in the engine. And there are different approaches and possible solutions for this problem, but we will be focusing on the application of diamond-like carbon coatings, also known as DLC coatings, which have already been applied in the automotive industry for more than a decade now. And here we have some images of real engine components that are coated with DLC materials. Now, DLC refers to a wide variety of materials that are usually represented here in this very well Robertson's diagram, where we can see, for example, tetrahedral amorphous carbons, which are very rich in sp3 carbon, very hard and very stiff like diamond. Then we also have amorphous carbon, which are more rich in sp2 carbon. And there are also diamond-like carbons that contain hydrogen, for example, amorphous carbon hydrogenated and tetrahedral amorphous carbon hydrogenated. Now, the problem here is that because these materials are being applied in the internal combustion engine, they are lubricated with traditional engine oils. And these engine oils contain a lot of different additives that were specifically designed to function in steel surfaces. And their effect on the tribological behavior of DLCs is still not very well understood. So the main goal of this study is to focus on a main ingredient of basically every oil formulation, which is ZDDP, zinc dialkyl dithiophosphate, due to its incredible anti-wear and antioxidant properties. And so we want to study what is its effect on the tribological behavior of DLCs through experiments and atomic simulations to understand the underlying mechanisms at the micro and nano scale that are responsible for microscopic tribological behavior. And when we look at the literature, I'm not going to make a very large review here, but in general we can see that most studies agree that the wear resistance of DLCs is mainly governed by the type of DLC, and even though thin ZDDP-derived tribofilms may form on their surface, the role of ZDDP as an anti-wear agent is negligible. In this study, we worked with 5 types of DLCs. The first is an ACH, which contains 20% hydrogen. The second one is an AC, which contains no hydrogen and very similar mechanical parameters, mechanical properties to the ACH coating. And then we have three different TAC coatings, and the number in parentheses corresponds to their hardness values in gigapascals, and it will help us to label these three different materials. As you can see, the first is obtained by a plasma-enhanced CVD procedure, and the non-hydrogenated DLCs are made by an arc PVD type of procedure. And instead of giving the roughness values before friction tests, here we're giving the roughness values after the running in. So here the root mean square height and the root mean square slope, which is the gradient of the height. The friction tests were performed using a reciprocating sliding tribometer, and we chose the cylinder on disc configuration to better represent line contacts in engines such as cam and follower systems or piston rings and liner contacts. The operating conditions were also chosen to represent, or at least to approach, the real operating conditions in internal combustion engines. And finally, we used a PaO4 base oil as lubricant and a PaO4 plus CDDP solution, where we include 1% weight of CDDP, which is equivalent to the amount of CDDP that can be found in real engine oils. And we used a primary C4 type CDDP, which you can see the structure here. So now I'm going to present the friction curves obtained in PaO for the 5 different DLCs, and we can see that for the softer ones, ACH and AC, the friction coefficient is about 0.10. And for the 3 harder DLCs, remember the number in parentheses is their hardness in gigapascals, we can see a significant reduction in friction coefficient, approximately of 0.02. Now, in PaO plus CDDP solution, there is basically no change in the friction curves of ACH, AC, and TAC51, as they are pretty much the same as with PaO. However, for the 2 harder TACs, we can observe that at the beginning of the test it is low, but then after a few thousand cycles, it progressively increases and stabilizes at 0.10. So some type of tribological mechanism is occurring here. And when we look at the wear tracks, we can see that in PaO they are very, very small, very smooth, so very little wear that has occurred during PaO lubrication. And when we look at PaO plus CDDP lubrication, and specifically at the 2 TACs that exhibit high friction coefficient, we can see that increased surface roughness and the appearance of horizontal scratches. And so when we look at the wear volumes that are measured by optical interferometer, we can see that for the 3 softer or less hard DLCs, the wear is practically non-measurable or very little, and for the 2 harder DLCs, we can observe high wear in PaO plus CDDP solution. So if we take a closer look at this wear track here, we can see that the wear depth of the flat is 0.5 microns and 1.5 microns for the cylinder, and keep in mind that the coating's thickness is 2.0 microns. So in this case we are approaching almost complete failure of the thickness. So if we were to summarize, it can be seen based on these results that the friction and wear properties of ACH, AC, and TAC51 are basically not affected by CDDP. However, CDDP has a catastrophic effect on the wear and friction properties of TAC66 and TAC78. So now the question is why? We performed contact mechanics simulations where we recorded AFM topographies after running in, so typically between 500 cycles to 2000 cycles depending on the friction curve. And we made sure that the images were recorded when friction was low and wear had not still begun. And so the cylinder and disc surfaces are brought into contact by application of an external pressure that is equal to the pressure used in the sliding tests. However, even though the macroscopic or Hertz pressure is the same for all DLCs, there can be differences at the local pressures at contacting asperities. So in this first panel, we can see the probability density and as a function of the pressure that experience asperities. And we can see that for the blue, green, and yellow curves, the probability density decays very rapidly, which means that most asperities undergo a pressure of only a few gigapascals. And when we look at the probability densities of the hardest TACs, so in red here, we can see that the distribution is much broader and that a large amount of asperities are reaching pressures of almost 30 or approaching 40 gigapascals. So in the next panel, we take the median values of these curves and we plot them and define as the local effective pressures against the material parameters elastic modulus and RMS slope, which were measured from the AFM topographies. In this case, the RMS slope is defined as the gradient of the RMS height value roughness. And we can see that for these three DLCs, the local pressures at the asperities are very low, or close to between 2 and 4 gigapascals. And for the two hardest TACs, the effective local pressures at asperities are almost or around 10 gigapascals. And this mechanical aspect that is different from the behavior of the other DLCs is associated to high wear and high friction. So we obtain a first hint of a mechanical aspect that could be responsible for this tribological behavior. Next, we proceed to study the surface chemistry of the wear tracks by XPS analysis, X-ray photoelectron spectroscopy. In this graph, we can see the atomic concentration of phosphorus, sulfur, and zinc for the 5 different DLCs measured inside the wear tracks of the disk samples. We can see that for ACH and AC, the concentrations are higher than for the 3 TACs, which are about 1% of atomic weight. And so we also studied the chemical states, so the chemical bondings in the wear tracks, and we can see that for carbon, oxygen, phosphorus, and zinc, the binding energies between the different DLCs are pretty much exactly alike, meaning that their chemical states is very similar and there is no difference. However, this is not the case when we look at the sulfur chemical state, where we can see here, for example, for the ACH, that the S2P spectra is composed of one contribution, which is presented here as 2 peaks due to spin-orbit coupling, and the binding energy corresponds to sulfur and zinc bonds or sulfur and phosphorus bonds, which already exist in the ZDDP molecule. When we look at the other DLCs, we see the appearance of a second contribution represented here in red, which corresponds to sulfur-carbon bonds at 163.3 eV. And we see that for the two hardest DLCs that exhibit wear, the red contribution actually is the dominant chemical state of sulfur in respect to the, in this case, weaker blue contribution. So basically, we observe a correlation between wear and the chemical state of sulfur. For the DLCs where the blue contribution is the dominant, and so the sulfur-carbon to sulfur-zinc ratio is low, we observe no wear. And for the TACs that the red contribution is dominant, then we can observe high wear and high friction. And now we have a second hint, but now from a chemical point of view, to explain the different tribological behavior between these TACs that exhibit high wear and these DLCs that do not. Next, we studied the formation of ZDDP-derived tribal films by scanning electron microscopy and EDX analysis. And for TAC 66 and TAC 78, we can observe the horizontal wear scratches already previously shown in the wear tracks, and no formation of tribal film is observed. We can only find find some small particles here that are derived from ZDDP, and their composition was verified by EDX punctual spectra. And when we look at the other three DLCs, ACH-AC and TAC51, we can see the formation of tribofilms that are consisting here of these ZDDP patches that are of their diameter varies between a few hundred nanometers to 5 micrometers for the largest ones, and are represented here in green by the chemical map of zinc. We can also see that the surface coverage of ACH and AC is higher than the TAC51, which is in agreement with our quantitative results observed by XPS. Next, we perform focused ion beam milling and transmission electron microscopy analysis, and here we study the tribofilm formed on an ACH surface, and we can observe that it is about 20 nanometers high, tall, which is about 5 times smaller than a ZDDP tribofilm that is formed on a steel surface in similar sliding conditions. And we performed EDX spectra analysis to confirm the presence of zinc, phosphorus, and sulfur in the tribofilm, and we represent them here with the chemical maps of carbon in blue, platinum in red, and zinc in green. I should add that platinum is deposited during the VIV process, and it's used to protect the samples before milling. So next we observe the opposite case. So for TAC66, where we didn't observe formation of tribofilms and when high wear occurred. So here we have a combination of 6 different images that are superimposed here, and we can see that there are two main features. On the right here we have a very large groove, empty groove, and here on the left we have what seems to be a very similar groove. However, it appears to be filled by a wear debris or redeposited particle. So when we analyze this area here marked in red dashed squares, we can see that if we follow this red arrow, originally this asperity tip was attached here at the TAC. However, due to friction, it was plastically deformed and detached, and this led to the propagation and formation of a crack that propagated into the matrix of the TAC. And here we can see a very clear boundary line which separates the redeposited particles observed in this region here from the typical amorphous structure of the TAC beneath the boundary line. Next, we proceeded to analyze the chemical composition of these different zones here, so represented in the yellow square, and we performed EDX spectra in these white or bright regions, and then compared them to the gray regions that correspond to the native structure of the TAC. And what we found is that in this green spectra here, we found high amount of sulfur that was diffused into the subsurface of the DLC. And if we look at a higher magnification image that was made here in this purple square, then we can see that in spectra number 5, this is the typical amorphous structure of the TAC, and in the region where we identified sulfur, so spectra number 2, 3, and 1, we can observe a friction-induced structural transformation from amorphous carbon into a more graphitic-like structure. Even we can see the formation of an onion-like type of structure here. And this phenomena of sulfur diffusion into diamond nanoparticles and formation of onion-like structures has already been seen before by Berman and colleagues. Although in their case, this phenomena occurred at the sliding interface and led to superlow friction, whereas in our case, this phenomena is occurring not only at the sliding interface, but also in the subsurface of the material, and is causing wear and high friction, so quite the opposite tribological effect. So to further investigate this phenomena, we performed MD shearing simulations of sulfur-doped DLCs, in which a shear stress is applied into a small atomic fraction of DLCs, where we introduce sulfur atoms, here represented in yellow, into the DLC matrix represented in gray color. And we can see that as the sulfur concentration increases, we have a decrease in tau, which is the shear strength of the material. In other words, sulfur concentration is weakening the material. And this phenomena has already been observed once before experimentally by Molsrado and colleagues, who produced sulfur-doped DLCs and noticed their mechanical properties being inferior to similar but non-doped DLCs. Now the question remains, how is this sulfur penetration occurring? And so we perform bond breaking and formation processes under tribological conditions by quantum mechanical molecular simulations here. And basically we take two DLC asperities, and we introduce a ZDDP molecule in between, and then apply an external pressure here to bring the two asperities into contact. And then we study at different times here the bond rupture and bond formation between ZDDP and the DLC surfaces. And basically, when we perform these simulations in a quasi-static manner without shearing, we can see that there is no difference between a hydrogenated DLC and a non-hydrogenated DLC. However, when we repeated these simulations, but this time not only under compression, but we add a dynamic aspect, so in this case we added shearing, now we can see a difference between an ACH and an AC. In the y-axis here we have the number of sulfur atoms that are released from the ZDDP molecule into the sliding interface. In other words, the degree of defragmentation of the ZDDP molecule as a function of the applied pressure here. And when we look at the pressure ranges in which the soft DLCs are located, so between 2 and 4 gigapascals, if you remember from the contact mechanics simulations, then we can see that less sulfur is being released, so the ZDDP molecule is being defragmented into a smaller degree compared to the two hardest TAC coatings that exhibit contact local pressures of about 10 gigapascals, and here we can see an increase in the released sulfur atoms and defragmentation of the ZDDP molecule. So this translates into a shear accommodation in a ZDDP layer that occurs for ACH materials, where we can see that the ZDDP is partially defragmented and accommodated in between the two ACH surfaces. However, for an AC surface, which is also representative in this case of a TAC surface at the topmost surface, in this case the ZDDP cannot be accommodated, and we actually see cold welding that occurs between the different surfaces. And this cold welding is measured by the amount of carbon-carbon bonds, and we can see that the cold welding increases drastically for high pressures close to 10 gigapascals. So the pressure ranges that correspond to TAC 66 and 78. And in these cases, after cold welding, we have sulfur diffusion and chemical mixing of sulfur and the other ZDDP additives that go beneath the surface, here represented by a lined black dot, and into the surface of the AC material. So basically, to summarize and to conclude, we can observe two different tribological behaviors. The first for soft and moderate hard DLC, so ACH, AC, and TAC51, where the material parameters of the elastic modulus and RMS slope are lower than 25 gigapascals, then the local pressures are low enough at the contact asperities so that ZDDP is only partially defragmented into two pieces here, and the formation of a ZDDP derived tribofilm is made approximately about 20 nanometers. However, for very hard DACs, where the material parameters of elastic modulus and the product of the RMS slope is higher than 25 gigapascals, then we have higher local pressures that are being applied here at the contact asperities, and in these cases we can observe cold welding and covalent carbon-carbon bonds between the different opposing surfaces, and this leads to chemical mixing, sulfur released, and ultimately an amorphous carbon sulfur doped material which is weaker than the original DLC material and leads to wear. So, as I said in the beginning, hopefully we can link the article information in the description below, and do not forget to like and subscribe if you're looking forward to more tribology related materials, and please leave your questions in the comment section below. Thank you very much.